Okay, the promise recording explaining the spreadsheet for the carjack project. So what is in red are input variables or inputs, calculated values. So this would be the maximum carjack load, 35% we said of the total weight of the vehicle. R1 is the base link shown here are two, the side links, they are all four equal. And then the maximum length of the screw, again, my values, and then I have the rate of shortening the screw, that's my negative value. And then other information about this power screw, so pitch diameter, lead, single thread, so it'll be equal to the pitch. The Acme thread angle, 14.5 degrees, and assume the friction coefficient between the screw and the nut. Okay, so some calculations here for efficiency of the screw, maximum power extract. So really what's in blue are a result of calculations. This one is the time it takes to fully lift the screw. I essentially divided by full length of screw by the speed. Of course, you cannot make this screw zero length, so that's why I subtracted, in my case, 1.5 inches. So really I divide the full length minus 1.5 inches. Minimum length could have been an input variable, but it's maybe on the future I'll change it. So anyway, 1.5 inches subtracted from full length of the screw divided by a rate of change of the length. Input a minus in to make a positive value. This will be the time for a full lift. Time column, so start from 0, and then I have 200 values for analysis and plots. So that means that the second time value would be previous one, 0 in this case, plus the time it takes for full lift divided by 200 of rows in the spreadsheet. Length of the screw starting with full length, and then it's going to shorten at this rate. So next column is previous plus, and don't forget is negative. Okay, so time, current time times velocity added to the initial length. But again, ds over dt, that is, this cell is the negative value, and then all the way down. And then from calculations, we've got the angle theta 2 in radians. You recognize this equation from a PDF that I shared with you. And I'm converting the angle into degrees. It's easier to interpret. And then height, current height of the jack. Again, from calculations, see the PDFs. And then we have also the, this implements both the principles of virtual powers, principle of virtual work, and statics of the side link. See the PDF. Okay, so these come from kinematic calculations. And then we have the load W, which we said it's going to have a profile to where it's negligible until we reach, and I have the values here. So in my case, first 8 inches of deployment of the jack, no load, and then between or starting with or between 8 and 13 inches, it goes progressively to maximum, and then 2 more inches full load. Okay, so this is what the column is. Actually, I put everything in an if function, and for maximum flexibility of the spreadsheet. So yeah, as you can see, if, and what I'm looking at these values here in the current y. Okay, so maybe you can zoom in and see my equation and how I interpret it. As we move along, it starts increasing, and then it settles to the W max graph is here as function of y. Okay, and then the corresponding load PS is force on the screw modeled here as a linear actuator. So this one implements the principle of virtual work. You can see it uses the white dot. This other one implements the statics of the side link. Values are totally identical, at least up to the first decimal. We can check and see if it goes beyond the, I think they do go beyond the first decimal. Okay, so torque to move the screw. This is the equation from your, it's the torque to move up the screw from the Design Machine Elements book. And so that's going to follow the same profile, or is it? No, it's actually different because of the non-linearity of the mechanism. And then the power in watts to move the screw, that is to shorten the screw. And this one, let's see, I used energy principles that and includes the efficiency, by the way. So the efficiency of the screw, it's in the Design Machine Elements textbook by Mott. So it's going to be the ratio between the work without or torque to move the screw without friction. It is this equals 0. And so if I make this 0, that efficiency goes to 1, of course. So, and then torque to move the screw against the load, that is to lift the load with friction. So power would be power at the screw. So I've got two implementations, one with velocity and working against the so velocity times force, it's power, and then corrected with the efficiency. The other one, and it's in watts, although everything else is in inches and English units. And this other one using the load, which is variable, and the velocity at which the jack moves up. Values are again identical or near identical. Actually, they are the same. Everywhere we look, you see the same values. Okay, so the two graphs here show a that is screw force is function of screw shortening. I reverse the x-axis because we start with the full-length screw. This other one shows the power in watts that's needed. There will be a maximum value around here, and that's extracted as maximum of, well, I said maximum power in watts. So we'll be on this column. I was careful to work with the shortening speed so that this power is reasonable. The electric motor that we'll be using to power the screw shouldn't be more than what I have here. Actually, looking at the to check the figures on blackboard, pictures of the jack, it says that is, I have actually the motor here. Let's see. Okay, so sorry for the break. I went to read the information of the, it's visible on the photograph, so it's 180 watts, the actual jack power. So yeah, we could go faster than 0.3 inches per second. We'll make this value. I can do this because of the flexibility of the spreadsheet, so okay, make it 0.4. Okay, of course the power went up. We lift the car faster, but otherwise this is your analysis. You would be interested in the maximum torque at the screw It'll be needed to size the last gear pair. We'll discuss in class, and maximum force in the screw. Of course, it changes with length for any buckling considerations. So I think this is it. I'll stop sharing. We're 49 minutes. Cannot believe that. Okay, thank you.